Hello, good morning. In my last class, we learned about the approximation methods. We learned what is approximation methods and when and whether we apply approximation methods. We learn approximation method can be applied whenever the problem has a similar problem which is exactly solvable. And perturbation or disturbance, whatever you may call, is sufficiently smaller than the exactly solvable part. And based on the exact solutions, perturbation method can be applied in order by order manner. For example, let us recall this matrix A. This matrix is subdivided in two parts. One is A0, which is 1 0 0 2, and another is A prime 0 epsilon epsilon 0. In these two parts, A0 is exactly solvable. You know, this matrix has eigenvalues 1 and 2, and A prime can be considered as perturbation provided off diagonal part epsilon is much smaller than 1. So in that case, we can apply perturbation method since A0 is exactly solvable. Okay, so let us now take some examples from quantum mechanics which has exact solutions. You know that one-dimensional quantum harmonic oscillator, a particle confined in rigid box, whether it is one-dimensional, two-dimensional, or three-dimensional, particle confined in square wave potential, hydrogen atom, all these problems have exact solutions. So now consider a harmonic oscillator, one-dimensional harmonic oscillator. So its Hamiltonian is like this. And we know its eigenvalues very well. So this Hamiltonian is exactly solvable. Now you add a perturbation to this Hamiltonian. So all this is perturbation, this is anarchonic part to this Hamiltonian. So if this perturbation is small enough, alpha is less than 1, then we can apply perturbation method to this problem. Okay. Similarly, we can consider a particle moving in one-dimensional rigid wall. So next consider this example, particle moving in one-dimensional rigid wall. B. Particle moving in a rigid wall. So we know its Hamiltonian, we know its eigenvalue is like this. Now you add a perturbation to this Hamiltonian, say like this. Now we apply a perturbation to this Hamiltonian, and if this perturbation is small, then we can solve by applying perturbation method. Similarly, hydrogen atom, we know its eigenvalue, but if the hydrogen atom is placed in a electric field, then we apply perturbation method if the electric field is small, sufficiently small. Similarly, take another example. So a magnetic atom is placed in a crystal, and let us take that atom is surrounded by ligands in octahedral coordination. So octahedral says here is a magnetic atom and a octahedral coordination. Is a atom in a octahedral coordination. So in this case, Hamiltonian is simply H crystal field due to these 6 ligands, and this is a magnetic atom. Now you place this crystal in a magnetic field, then this Hamiltonian will be H0 minus mu dot H. H is external field and mu is its angular moment, mu it is magnetic moment. So if this part, which is called Zeeman splitting, Zeeman energy is sufficiently small compared to the crystal field energy, then we can apply perturbation method. So these are few examples of how when we apply perturbation methods in quantum mechanics, and all these problems is similar to a problem which is exactly solvable. So all these systems, say a particle moving in rigid box, or a quantum harmonic oscillator, or a hydrogen atom problem, or a magnetic atom placed in octahedral coordination of ligands, all these problems, all these systems are bound systems. So in quantum systems, we encounter two types of systems. One is bound system and another is unbound system. So what do we mean by bound system? So bound system in the bound system, the particles are restrained by external force in a particular region. For these systems, total energy is less than zero. So in these systems, total energy is less than zero. And there is another system which is unbound system. Scattering or collision problem. In this case, the particle can approach and recedes away. So this, in unbound system, the particle can approach and recede away to infinite distance. This system or this problem is popularly known as scattering or collision problem. It is important to remember that most of the most direct information regarding the nature of force can be obtained from this unbound system. In this case, I can give a simple example taking from nuclear physics. You know that we all know the deuteron problem. You know that the deuteron is basically a neutron-proton system. So, neutron-proton system can be found in bound system in the form of deuteron, or can be found such that a neutron can impinge upon a system of protons and then it can be scattered. You know that if we apply Pauli's exclusion principle to a neutron-proton system, the states available to neutron-proton system is the states available to NP system, like this: 3s1, 3d1, 3p1, 1p1, 1s0, etc. These states are available to NP system if we apply Pauli's exclusion principle. Of these states, only 3s1 and 3d1, information about only 3s1 and 3d1 can be obtained from the ground state properties of deuteron. So others information about these states can only be obtained from the scattering problem, that is, scattering of neutron by a bunch of proton at different energy. So this is from deuteron, and these are from scattering. Similarly, proton-proton and neutron-neutron system, you can never find them in bound state. So to get information about the pp diproton and NN, that is dineutron system, we rely upon the scattering problem. Okay, so these examples I give only to understand why we study in quantum mechanics the problem of bound system and the problem of scattering. So scattering problem we learn in due course. So I can classify the approximation methods in tabular form. So we write quantum system, bound system E less than 0, and this is unbound system of scattering. Scattering, this can be divided into two. When potential energy is very larger than kinetic energy, and another is when potential energy is very less than kinetic energy. So unbound system. Now bound system. Stationary problem. Time dependent. Stationary bound system, the problem of bound system in terms of approximation methods. So we divide it in two parts, in stationary part, time independent part, and another is time dependent part. So stationary part I divide time dependent perturbation WKB approximation, variational method, So stationary approximation method is divided in three parts: time dependent perturbation, which I write abbreviated as TDPT, WKB approximation, and variational method. And time dependent perturbation method time independent. Time independent. TIP, time independent perturbation, WKB approximation variation method. So TIP, and this is time dependent perturbation, TDP, adiabatic approximation, and this is sudden approximation. Time dependent perturbation can also be divided into two parts: non-degenerate perturbation theory and another is degenerate perturbation theory. Non-degenerate perturbation theory, and another is degenerate perturbation theory. So we have to learn all these methods: time dependent perturbation, WKB approximation, variational method, and from time dependent part we learn time dependent perturbation, adiabatic approximation, and sudden approximation. So I think you know about the non-degenerate and degenerate case. So I take a simple example to understand what is non-degenerate case and what is degenerate case, and what will happen to a problem when we apply perturbation to a non-degenerate system and also to a degenerate system. So I take a simple example of a Okay, I take a simple example. Say this is a matrix A. This I subdivide in two parts, A0 and A prime. this I write as A0 and A prime. So A0 has only two eigenvalues. E1 is 1 and E2 is 2. So these are the eigenvalues of A0, and its eigenfunctions is 1, 0, and its eigenfunctions is 0, 1. So this is a case of non-degenerate states. Non-degenerate, so these eigenvalues are non-degenerate. Okay. So when we apply perturbation, without going into details of calculations, I can write the energy will be of this energy will be 1 minus epsilon square, and E2 is 1, 2 plus epsilon square. This is the energy. Okay. So if I write this energy in a graphical or form, so this is E1 is 1 minus epsilon square, and E2 is 1, 2 plus epsilon square. So if I write a schematic in figure, so this is energy, this is 1 and this is 2. So this difference is simply del epsilon is 1. Now after perturbation, this is due to the A0, this is due to A0. Now we apply a perturbation. So what's happened? This level is shift to downwards, and this level is shift to eastwards. So this is 1 minus epsilon square, this is 1 plus epsilon. So this difference now becomes 1 plus 2 epsilon square. So this difference becomes 1 plus 2 epsilon square. So see that after applying a perturbation to a non-degenerate case, it increases the splitting, energy splitting. Okay, so this is the so non-degenerate, so perturbation in non-degenerate case increases the energy splitting. Okay, so now you consider a degenerate case. Now we consider a degenerate case. This is non-degenerate case. So now we consider a degenerate case. Degenerate case. Simply now you take an example. A matrix A is 1 epsilon 1. So I subdivide this like simply matrix 1 0 0 1 plus 0 epsilon 0. So I write this is A0 and plus A prime. So in this case, this has a two eigenvalues. E1 is 1. Similarly, E2 is 1. So this is an eigenfunction is simply similarly this 1 0 0 1. So this is a degenerated case. So in this case, eigenvalue has twofold degeneracy. So eigenvalue has twofold degeneracy. Okay, so these eigenvalues are twofold degenerate, that is doublet. Okay, so now we apply perturbation to these eigenvalues. So what happens in that if you apply this perturbation matrix, then it becomes is E1 equal to 1 plus epsilon and E2 is 1 minus epsilon. This is the eigenvalue of this matrix. So you see that due to perturbation, the twofold degeneracy of these eigenvalues are removed. Okay. So I draw these eigenvalues in a diagram in like this. So you see that this is 1. So I give another line. So last two. So in this case, del E 0 is 0. So this is due to A0. Now you apply perturbation. So it becomes, so this is 1 plus epsilon and this is 1 minus epsilon. So this splitting is now becomes twice epsilon. So okay. So we see that due to perturbation to this doublet twofold degenerate eigenfunctions, the perturbation it removes the degeneracy and causes a splitting. Okay. So what we learn from this example for degenerate case? If we apply a perturbation, small perturbation, the perturbation removes the degeneracy of the eigenvalues of the exactly solvable part. Removes the degeneracy as well as it splits the energy level. So this is the difference between a non-degenerate case and a degenerate case when we apply perturbation method. In case of non-degenerate, I repeat again, in case of non-degenerate case, the perturbation increases the splitting between the energy levels or eigenvalues, and in case of degenerate case, it removes or leaves the degeneracy either fully or partially and splits the energy level. Okay, so in my next class we learn about the temperature independent perturbation method. And so goodbye to you all.